Good morning, everybody. Today I'm going to be talking through. I'm just going to go to chapter 3 and start doing some acids and bases because I think this is going to be a big component of your guys' exam on Friday. So let's spend most of today, probably all of today, talking about acids and bases. For the majority of this class, what we're going to be talking about is what's called Bronsted acids or Bronsted bases. Nope, no way. Never mind. And these can be simplified to essentially you're going to have some sort of acid which will have a proton on it. And some sort of base. And what's going to happen is your base is going to do an attack on this H here. We are going to grab the H, the proton, kick out the electrons that were in the bond, move them over to where the acid was, and we are going to form what's referred to as a conjugate base and a conjugate acid. So your acid will always become your conjugate base. And your base will always become your conjugate acid. You could also always think of it as the whatever has the proton here is going to be the acid in the situation. Whatever has the lone pair is going to end up being your base. Okay, so let's do a actual example. All right, so as you guys probably talked about in class, there are something called pKa's, which is going to be a gauge of acidity. There's also some general rules you can follow, and I'll go over those also. In general, an OH is going to have a pKa of roughly 16, and amine here would have a pKa of roughly 35. Because The pKa of the amine is higher. That's going to make it more basic. More acidic here. So what we could have happen would be this nitrogen, which has a lone pair on it. Blend the color. Could potentially grab the proton off of this hydrogen here, or this oxygen here, kicking the electrons to the oxygen, giving us this ammonium here, as well as this alkoxide. So in this situation, we had our base was our amine here. Our acid was this alcohol, which means that in our product, they're going to be flipped. So our conjugate base will be our now deprotonated alcohol. And a conjugate acid will be this deprotonamine. All right, so as we said, there's some general rules. For figuring out what is going to be more or less acidic. And those generally fall into a category people like to refer to it as areo. A being atom size, R being resonance, I being induction or inductive effects, and O being orbitals. There's another one that kind of goes into atom size, which is charge. I'll talk about that a little bit. But let's generally just start with atom size. So when we are looking at two molecules, let's say bromine and iodine, they're both on the right side of our periodic table. Let's do chlorine and iodine. So if we look at our, oof, I don't have a periodic table pulled up, but I can draw out that. Second to last column, we're going to have fluorine, chlorine, bromine, iodine here. So iodine is going to be our larger molecule, and therefore it's going to be more stable when it loses a proton. And that's going to be a lot about what this acidity is based on. So iodine can go to I minus. So can HCl. You can lose that proton. In either case here. And the reason why iodine is even more stable is really kind of just like a fraction rule. If I think about iodine's atomic number is 53. Versus chlorine's 17. Which that means when we make this chlorine minus here, we added an extra electron, which means you have 18 out of your 17 electrons. Versus with iodine, you'd end up with 54 out of 53 electrons. So the overall charge difference is a little bit smaller. It's a lot easier to distribute. I don't know what percentage this is, but it's quite a small difference versus here where you're ending up adding a lot more like total charge to your molecule, because you're going to have 53 protons to balance out your 54 electrons in the iodine. You only have 17 protons to balance out the 18. I'll probably do the math on that. So for chlorine, you added 6% more charge, versus for iodine, you only added 2% more charge, which is why the iodine is so much more stable. So when we have a problem where we have both of these in solution, like this here. So this is a basic acid-base formula here. We're going to have our two different acids. So on the right, I'm just going to call it the normal acid, and the left, I'm going to call it the conjugate acid. Nope, I said that backwards. This is the base. This is the conjugate base. The question you're typically asking yourself with these is which side is more stable? If you're just trying to figure out which one is better and you don't have any sort of pKa tables. So for this here, usually it's easier to just kind of look at the base. So HI went to iodine, or if you're going in the opposite direction, HCl went to chlorine here. You know that iodine is your larger molecule. It's going to be more stable with the charge on it. And because of that, you're able to know that this reaction is going to favor going towards the right here. It's going to go towards favoring your most stable base. That's a good way of thinking of it. We can do another example. Let's do one similar to the thing we talked about before. So not really know the direction. Okay, so generally speaking, if you have a negative charge, that tends to be your base. So for this example on the right, if we look at what's happening in this reaction, on the going from right or left to right here, we're picking up an H at our oxygen position, which means that the H would have been donated from the other molecule, which means that this is going to be the acid, because this is what's going to be donating the H. You can also see that it's missing one on the other side. Our base is going to be the other component of it, and then on the opposite side here, it'll always be the opposite, so this would be our conjugate acid. Then our conjugate base would be this amine here. Okay, so we have comparing our two different conjugate acids or our two different conjugate bases. We've got a nitrogen, and over here we have an oxygen. So that means if we go to our periodic table, oxygen is the larger molecule. Which means it is better for holding charges. So it's going to favor the position where the oxygen goes to the O minus. So over here, this is what's going to be more stable. And our reaction is going to favor going to the left here. So a couple of different ways you can think of it. You can think of it as you're always going to be going away from the acid that's more stable, or always going towards the base that's more stable. Or the acid of the larger atom, or the base is more stable. But they'll always be like the conjugate version of it. So I'm going to draw one or two of these up and have you guys walk through them, and then we'll talk through resonance. Okay, so take a few minutes, mark which one you think is the acid of the base, the conjugate acid of the conjugate base, and then which direction the reaction should go in. All right, so let's take a look at this. Our acid is going to be our proton donor. So taking a look, this H here ends up going to this position in our other side of our formula. So that is going to be the proton that's being donated. So this would be our acid, making this our base. If we know one, we are able to figure out the other ones. So that means our conjugate base is going to be what our acid was. Let's see, it should be our conjugate acid. Comparing the two of them, we have a bromine versus an oxygen. Comparing our two acids, which means bromine is larger. It's going to be going towards having that be deprotonated or going towards bromine's basic form. So this reaction should proceed to the right here. Looking at our bottom equation, we've got a proton on our alcohol here. It ends up on our thiol on the other half of it, making the proton that's being donated this proton from the alcohol. So this should be our acid. Making this deprotonated thiol our base. Conjugates are going to follow the same pattern. So conjugate acid will be what our base was. Conjugate base. Will be this thing on our OH here. All right, looking at our periodic table, sulfur is larger than oxygen, which means it should favor sulfur being deprotonated. And this reaction is going to proceed to the left here. Are there any questions on this? Okay, let's do atom size, or not atom size, we just did atom size. Let's do resonance. The resonance is pretty straightforward. You need to be comparing the same atoms, generally speaking. So let's start with this proton here versus this proton here. So if we pull off the proton on the left, we would generate a CH2 minus versus if we pulled off the one on the right here, we're still going to make a CH2 minus. It's just now that this charge exists in two places. It can exist here, but it can also do resonance to exist here. So between these two, this is your more stable base. If we have the option for multiple, oops. For instance, these two, if you deprotonate them, this one on the left will have two resonance structures. Versus the one on the right here. which can have 3 different resonance structures. The charge is going to be more distributed across your bonds. And therefore, this one on the right is again more stable. Another way you'll often see this is you compare an alcohol to a carboxylic acid. So I want this to not be decoordinated yet. If we add base and solution for both of these, we make an O minus. On both sides. But our oxygen on the right has the ability to do resonance. And share that charge between the two positions. So you can think of it as 100% of the charge is going to be on the oxygen, in this case on the right, versus this case on the left, 50% of the charge is going to be on this first oxygen, and the other 50% is going to be shared with a second oxygen here. So the one on the left is, or sorry, the one on the right is going to be a lot more stable.
So if it's more stable, it's more likely to dissociate, right?
Yes. If it's more, like if your base is more stable, that means your acid is more acidic.
All right, thanks.
Yep. All right, so I'm going to draw 2 of these up, have you guys go through them, and then we'll do some induction. Should have made more room. Okay, so go through again. Label your conjugate acid, base, conjugate acid, conjugate base, and then which direction the reaction should go in. Oh, missing some double bonds here. Okay, I think that should be good. All right, so taking a look at this first one here. We have this proton here, which is being transferred to over here, making this our conjugate or acid on the far left. This should be our base. If that's our acid, this will be our conjugate acid, or conjugate base, sorry. This will be our conjugate acid. Looking at the two bases, base number 1, we could potentially move our electrons here. So there'll be one resonance form. We could then shift them to here, and then finally to here. So there'll be 1, 2, 3, 4 potential places. That our resonance structures could go to. Looking at the one on the right here, we could have the electrons go to the left to get to a resonance structure. they could also go to the right to get to a resonance structure, meaning that there are only 3 resonance structures. Making the one on the left the more stable one. We're going to want to go towards our most stable base. So this reaction will favor going to the left. All right, our next one here, we've got this H, which is being transferred to our carboxylic acid here. So this should be our acid, this would be our base, making this our conjugate acid. Conjugate base. The acid currently has no resonance structures. If we're looking just at the left, the base has 1 resonance structure. So that's the one that should be more stable. So this reaction will favor going also to the left here. Any questions on this one? All right, if not, I'm going to have you guys turn on your cameras, take out a blank sheet of paper, and we will go through today's quiz. So you'll be drawing resonance structures for these 3 molecules. Use arrows to indicate where they should be going. I can give you guys about 2 more minutes.